Hello and welcome to today's lesson on non-optical telescopes, which is found in the Astrophysics section of the AQA A-Level Physics. So in today's lesson we're going to try and understand the properties of the different non-optical telescopes found in astrophysics. So if we are successful and we learn in today's lesson, we can understand how radio, infrared, ultraviolet and X-ray telescopes work, describe the differences between optical and non-optical telescopes, and then compare the different types of resolving power and collecting power found in different telescopes, which falls into the following part of the AQA A-Level Physics specification in the option block of that particular course. So, stellar objects emit all forms of electromagnetic radiation which we can detect. This occurs as stars can be considered as blackbody radiators, and blackbody radiators are radiators which emit all wavelengths of radiation. Now, this is a diagram of the electromagnetic spectrum. It's not actually to scale because in reality the visible part of the electromagnetic spectrum makes up a very, very small proportion of it. Now, the majority of the electromagnetic spectrum is actually in the radio part of the spectrum, and the optical telescopes can only detect radiation from the visible section, which is an issue because this means all this non-optical part of the spectrum we've got to use non-optical telescopes so we can detect all the radiation from stellar objects. Now, it's very important to astronomy as the majority of radiation emitted by stars and galaxies is non-optical. Now, each telescope used to detect each type of radiation must be modified to suit the properties of that particular radiation. Now, like we mentioned before, the most common non-optical telescope is the radio telescope. So we've got to be able to detail the different telescopes used to detail all parts of the electromagnetic spectrum. Now, as we mentioned before, because a large proportion of the electromagnetic spectrum is radio waves, the most common non-optical telescope used in astronomy is the radio telescope. Now, the UK is home to one of the largest radio telescopes in the world, which is the Lovell Telescope at Jodrell Bank, situated in the northwest English countryside. Now, radio telescopes are very similar to optical telescopes. The radio telescope has a primary concave dish, which is very similar to the primary concave mirror of the reflecting optical telescope. Now, ground-based observations are severely affected by the atmosphere for most of the electromagnetic spectrum. Now, actually, two of the regions of the spectrum least affected by the atmosphere is the visible wavelengths and the radio waves, which allows us to have radio telescopes based on the ground on Earth. Now, the primary concave dish can be made of mesh wire. This is because the radio wave does not have to be optically reflected like it does in an optical telescope, so it doesn't have to be made from glass. Now, this is because radio waves have a longer wavelength than visible waves, so the dish does not have to be made as precisely as an optical telescope does. Now, using metal wire decreases the weight of the telescope and the cost of the telescope compared to making this dish from glass. Now, the primary concave dish reflects the waves to a focal point. Now, at this focal point, an antenna is placed there as a detector. So you've got your parabolic dish, which reflects the radio waves, and your antenna, which is there to detect the actual image which is formed. Now, unlike the Cassegrain arrangement, there is no need for an eyepiece lens in a radio telescope to form an image because it's non-optical, so you don't need that lens there to form an image for the detector. Now, radio telescopes are also very maneuverable because it allows the source of the waves to be tracked by the telescope. Now, sources will move across the sky due to the Earth rotating, not to the source itself moving. Now, man-made interference can also be a big problem for radio astronomy. Now, radio transmissions, mobile phones, radar, global navigation systems, satellite TV, and even microwave ovens found in people's kitchens all contribute to making the detection of extraterrestrial radio-emitting objects very difficult. So it's difficult to deal with the interference from orbiting satellites, but the effect of microwave ovens, for example, is minimized by building radio telescopes away from the centre of populations, which is why, for example, Jodrell Bank is found in the Cheshire countryside and not in the middle of Manchester. Now, radio telescopes can also be used during the day as well as night because there's no interference from visible radiation. So unlike your optical telescopes, it can work for 24 hours a day. Now, radio waves are much longer than visible light waves, so if we use the Rayleigh criterion to look at our minimum angular separation, this indicates to us that our radio telescopes have a very poor resolving power, because lambda, the wavelength, is very large, so our minimum angular separation is going to be large. So the resolving power of radio telescopes tends to be quite poor, so this can make it hard to identify the source of radio waves which we detect from space. So for example, in the early 1960s, a lunar occultation was needed to identify a particular source of radio waves, which led us to the identification of the first quasar, which we'll look at later in the course. Now, for a radio telescope to have the same resolving power as a standard optical telescope, it needs to be about 1,000,000 times bigger. This is because the radio waves have a wavelength 1,000,000 times bigger than the wavelength of visible light, so the diameter of that telescope would need to be 1,000,000 times bigger. So a radio telescope would need to be approximately the same size as the United Kingdom to produce the same resolving power as a standard normal optical telescope. Now, the resolving power of a radio telescope is actually worse than the unaided human eye. So to overcome this issue of radio telescopes having a poor resolving power, astronomers link lots of radio telescopes together. So an example of this is the Very Large Array found in New Mexico in America. So astronomers combine the data from many different telescopes to form a single image, and we can consider the diameter of the telescope to be the distance between the different telescopes. So this gives us a resolving power actually 1,000 times better than those of optical telescopes. Now, linking telescopes together also helps, as local interference can be removed from individual detectors, enhancing the common signal from distant sources. So, radio telescopes are much easier to construct than optical telescopes. Reason number one, the construction of a dish from wire mesh is cheaper and easier than glass. And reason two, the longer the wavelength of radiation being detected, the less it's affected by imperfections. So as a result, you don't have to be as precise when you make your parabolic dish for your radio telescope as compared to your optical one. So this means radio telescopes never really suffer from spherical aberration. Now, provided the mesh size is smaller than lambda over 20, radio waves are reflected rather than diffracted through the mesh, so therefore the shape of the dish has to have a precision of approximately lambda over 20 to avoid spherical aberration, which for a radio telescope, where lambda can be in the order of millions or thousands of meters, that can give a very large value. So here's just a schematic diagram for a radio telescope. Now, just to note, the design of a single dish radio telescope is very similar to that of a reflecting optical telescope. The parabolic metal surface or reflecting dish reflects the radio waves to an aerial without any spherical aberration. There is no need for a secondary reflector, as the aerial can be placed at the focal point and the information is then transmitted for analysis. Now, a preamplifier amplifies the weak radio signals without adding too much noise to the signal as well. Now, we've looked at our radio telescopes, now let's look at our infrared telescopes. Now, infrared telescopes are very similar again to optical reflecting telescopes. These telescopes use a primary concave mirror to focus the radiation onto a detector. Now, the detector must be what we call a charge coupled device, because the radiation is non-optical, you cannot see it. Now, infrared radiation has a longer wavelength than visible light. This means, like the radio waves, the mirror does not have to be as parabolic as optical telescopes, because the longer the wavelength, the less the radiation is affected by imperfections in the mirror shape. However, the issue with infrared telescopes is that they, like all objects, emit infrared radiation. This means they will provide interference on their own readings and cause a blur in the image. So to minimize the interference of the infrared radiation coming from the telescope itself, the infrared telescope must be cooled to very low temperatures using either liquid helium or a refrigerating unit. Now, another issue you find with infrared telescopes is that infrared radiation is absorbed by water vapor in the atmosphere. This means the infrared telescope should be placed into space to avoid this effect. Now, an infrared radiation telescope would detect very little little if it was placed on the surface of the Earth in normal conditions. So we can see this in this particular graph. It shows us that our infrared radiation is absorbed by the water vapor in our atmosphere, H2O. But it's also interesting to note that there are some infrared spectral windows where the atmosphere is transparent to infrared wavelengths and objects can be observed from the ground or at an altitude with very little absorption. So these windows lie at approximately 3 to 5 micrometers and 7 to 14 micrometers. Now, the issue with placing our infrared radiation telescopes into space to avoid the water vapor absorbing the infrared radiation and blurring or minimizing our image is that it's very expensive to do this. And in addition, you need much more detail to correct and maintain in space. So the issue is that many space-based infrared telescopes cannot have their missions extended as they can't have their coolant replenished in space because it's very difficult to actually go up there and fix it or correct any issues. But we can, if we want to, place an infrared telescope on an aeroplane or a weather balloon, because the aeroplane and the weather balloons go above the water vapor found in the atmosphere of the Earth, or you can place them high on a surface of the Earth high up in a dry place. So for example, there's an infrared telescope facility found in Mount Kia in Hawaii, which is going to be a very high mountain, and it's in a very dry place. There's very little water vapor in the atmosphere. Or for example, in the Atacama Desert in Chile. Once again, it's at a high altitude, so it's above lots of the clouds, and also it's a very dry habitat. So as a result, there's not much water vapor in the atmosphere at these particular places on Earth. Now, once we've looked at infrared telescopes, we can now look at UV telescopes. Now, UV telescopes, again, are very similar to optical reflecting telescopes. These telescopes use a primary concave mirror to focus the radiation onto a detector, and the detector must be a charge-coupled device as the radiation is non-optical. Now, this is quite important, that UV radiation has a shorter wavelength than visible light. This means the mirror needs to be more parabolic than optical telescopes, because the shorter the wavelength, the more the radiation is affected by imperfections in the mirror shape. This means it's very difficult to manufacture UV telescopes. Now, another issue with UV telescopes is that UV radiation is absorbed by the ozone layer, O3, in the atmosphere. This means a UV telescope should be placed in space to avoid this effect. So a UV telescope would detect very little if it was placed on the surface of the Earth, which is shown in this particular diagram. As you can see, the O3 is absorbing all of the ultraviolet radiation. So, as the UV radiation is absorbed high up in the atmosphere because the ozone layer is very high up, this means placing a UV telescope on a mountain would be pointless because it would still be below the ozone layer. So it's better that UV telescopes are strapped into high altitude weather balloons or aeroplanes to overcome this problem, or you can place them into orbit in space. However, like mentioned before, it's very expensive to carry out and maintain, and this is important because many telescopes operate beyond their expected time, and modifications can be made to correct faults either by direct intervention with the Hubble Space Telescope or by modifications with mission objectives as with Kepler. So we've got to think about this if we place a UV telescope into space. Now, the next telescopes we're going to look at are X-ray telescopes. Now, X-ray telescopes do not work like optical telescopes because X-rays do not reflect off radiation like other forms of radiation. X-rays either transmit through a material or are absorbed by a material. This is shown in radiographs or X-rays. The X-rays are either absorbed or they're attenuated by the materials of the body, forming that X-ray image. Now, X-rays will, though, reflect slightly off a surface if they just graze a surface. However, this only slightly changes the path of the X-ray. It's like skimming a stone off the water. So what we do is the X-ray telescopes have a series of nested mirrors, and what these nested mirrors do is they slightly graze and graze and graze and graze the X-rays, changing the path slightly, so over a long period of time the X-ray is gradually brought to a focal point. So each grazing gradually alters the direction of the X-ray until they're all brought to a focal point. So another name for an X-ray telescope is a grazing telescope. So for example, the XMM Newton telescope has a series of 58 nested mirrors which gradually alter the direction direction of the X-rays. Now, X-ray telescopes tend to use charge-coupled devices or Geiger counters as their detection for images. Now, X-ray radiation is absorbed by the atmosphere, so like other particular telescopes, X-ray telescopes should be placed into space to minimize this effect. So the X-ray telescope would detect very little if it was placed on the surface of the Earth in normal conditions. And as the X-ray radiation is absorbed high up in the atmosphere, placing an X-ray telescope on a mountain would be pointless, so you can strap your X-ray telescope to a high altitude weather balloon or aeroplane to overcome this problem, but the ideal solution is to placed in orbit in space. However, like we mentioned before, it's very expensive to carry out and maintain. Now, in fact, some of the earliest satellites which we placed into space were used to carry X-ray and gamma ray detectors, and the detection of these high energy photons allowed analysis of the most violent and extreme phenomena in the universe and provided data about the age of the universe, the expansion rate of the universe, and the composition of our universe. Now, interestingly, even though gamma radiation is absorbed in the atmosphere like X-rays, there are still telescopes used to indirectly detect this radiation on the ground, because the occurrence of gamma ray bursts is another aspect of astronomy which has caused controversy, and the detection of the particles and radiation produced by these gamma rays produced in gamma ray bursts when they hit the upper atmosphere allows for ground-based observations. So many modern telescopes are put into space, and there are three main reasons for this: the absorption of the electromagnetic waves by the atmosphere, the light pollution and other interference at ground level, and the effect the atmosphere has on the path of the light as it passes through. Now, whilst we've talked about the different types of non-optical telescopes, we've got to look at also the detectors of these telescopes. Now, all telescopes must be connected to a detector to register the images collected by the telescope, and the most common type of detector is something called a charged coupled device, or CCD. Now, a charge coupled device is a series of silicon chips which are about the size of a postage stamp. Now, each silicon chip is divided into millions of identical picture elements or pixels. You tend to find the standard CCD has 16 million pixels on its particular frame. Now, the number of pixels on a CCD determines its resolving power. The greater the number of pixels per area, the greater the resolving power. Now, each pixel can be considered a potential well of electrons. So this is a schematic diagram showing the electrodes acting in the pixel to maintain trapped electrons in a potential well. So the charge coupled device works via the principle of the photoelectric effect. So let's consider one pixel on a silicon chip of a charge coupled device. Photons of light from stellar objects are incident to the silicon chip. If the photon has more energy than the work function of the silicon, then the electron is released. Now, the amount of charge found on each pixel builds up over time to form an image on the CCD. Now, the dividers, or the electrodes of the pixels, traps the charge so it's retained on that particular part of the charge coupled device. The electrodes will then move the electrons in order for the information to be processed, so when the exposure is complete, the electrodes are used to shovel the electrons along the array so the contents of each well can be measured, and the charge measurement is then used to create an image. Now, as some photons will hit your CCD but not have enough energy to overcome the work function and release the electron onto the silicon chip, this tells us that not all incident photons register an image on the CCD. So the number of electrons trapped in each well of the CCD is proportional to the number of photons hitting the plate, i.e. to the intensity of the light falling on the pixel. So this means the pattern of electrons in the array is the same as the image pattern formed by the photons, but not every single photon will release an electron. So the percentage of registered photons compared to the total photons incident to a device is called the quantum efficiency. So quantum efficiency is the number of photons registered, i.e. the number of electrons released onto the silicon chip, divided by the total photons which hit your CCD times by 100. Now, the quantum efficiency of a CCD is approximately 80% or higher, whilst the quantum efficiency of your eye is about 1%. So straight away you can see an advantage of using a CCD as your detector on a telescope as opposed to a human's eye. Now, another problem with eye eyesight is that at low light levels there's a loss of colour vision as the colour sensitive cones no longer work and light detection is taken over by the rods. Now, another thing is that if we leave a charge-coupled device for a long time, a large charge can build up with lots of electrons being released. So this allows CCDs to detect faint images which eyes could not detect. So this means the exposure time for a charge-coupled device is much longer than that of the eye, so you can see much fainter images. However, there is an issue that if the charge-coupled device is exposed to too many energetic photons, then the charge can spill over the dividers and onto different pixels, which we call in astronomy bleeding. So this can cause an image to be smeared on your actual detector. So for example, these are very, very bright stars and they aren't actually in that particular pattern. There's a smearing effect caused by the electrons released on that particular pixel flowing over and bleeding onto other pixels, forming that particular effect you can see. So we can compare now the two main types of detectors found in astronomy, the CCD and the human eye. So the CCD has a quantum efficiency of 80%, whilst the human eye has a quantum efficiency of 1%. The CCD can detect all parts of the electromagnetic spectrum because all photons can be registered by it, but the human eye can only detect the visible parts of the spectrum. Now the CCD has a spatial resolution of 10 micrometers, whilst the human eye has a spatial resolution of 100 micrometers. So the CCD has a higher resolving power and the human eye has a lower resolving power. Now, in addition, another advantage of a CCD is that you can copy, share and distribute images easily, especially in the more high-tech modern world now. So once a CCD registers an image, that can be sent via the internet to any other scientist around the world. Now, with the human eye though, is cheaper and much simpler to use than in fact the CCD, because all you've got to do with the human eye is look through the telescope as opposed to setting up your CCD. Now, just to clarify, spatial resolution is the minimum distance between objects which allows the objects to be seen as two different objects by the detector. Now, a CCD has a higher resolution as the objects can be situated closer to each other and still be seen as separate objects. So this is due to the number of different pixels on a CCD. So basically, the number of pixels per centimeter squared is a lot higher on a CCD compared to the number of light receptors per centimeter squared and the retina of the human eye. So, if we've been successful and we've learnt in today's lesson, we understand how radio waves, infrared, UV and X-ray telescopes work, we can describe the difference between optical and non-optical telescopes, and we can compare the different resolving powers and collecting powers produced by the different telescopes. So, we can state the similarities and differences of radio telescopes compared to optical telescopes. We can discuss the structure, position and use together with the comparisons of resolving power and collecting power. We can then have the comparison of the eye and the CCD as detectors in terms of quantum efficiency, resolution and convenience of use. So, I hope you've enjoyed today's lesson on non-optical telescopes in the Astrophysics option module of AQA A-Level Physics, and have a lovely day.